Hello everybody, welcome back to From Rhythm to Algorithm, part 47, counting. We're just again, talking a lot about iteration, trying to formalize that as a mathematical function or describe how it's a extension or relation of the mathematical operator multiplication, right? Integration is to addition, multiplication is to iteration, to do many times. So we're just going to try to review and really just start at the base, of what counting is, right? We're all people, we all live in an environment, we all processed information from that environment before we could literally formalize and speak words as children. So we all interacted with objects well before we spoke. And we also, right, you play with blocks and you play with different things as children. So the first thing I want you to do is just imagine you have, I'm going to try to be specific on the language, but just trying to get through the logic. Let's say you have 10 equal, completely uniform ovals, three-dimensional ovals, just little, not balls, but ovals, in your hands lined up in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe dolls on a windowsill, just really any physical object. But what can we say about that? That's our starting point. That is where we are at. What can we say about that, and how does that relate to counting, to iteration, to beginnings, to ends, to starting, to finishing? What we've been doing a lot in this lecture series is talking about the one-way evolution of the physical universe, and I'm trying to develop a novel proof. But R3, all measurements have been in, since light has stabilized, since matter has stabilized. This is a finite local set. And when I keep saying there's a limit to range, I'm sure, at this point, I'm 95% mathematically confident base and range are finite, and iteration is infinite. But in the very beginning, just review, we said series contain operations, addition, multiplication, subtraction, iteration, division, exponentiation, all of those. And just as a geometric note, again, obviously the addition sign symbolically and the multiplication sign are 90-degree rotations. The X is kind of like 4 V's. And sequences do not. Sequences are just lists of numbers. And right, if you go take an IQ test or something, you'll just, what's the pattern in this sequence of numbers? And you'll try to derive the series. So how does series and sequence relate to function? I don't know, random thought, not the point. My point is just that's a review from the beginning episodes. But now in physics, we say observation, or we say renormalization. You said, ask any physicist that is competent right now today, why doesn't gravity, or why doesn't general relativity is not compatible with the standard model of particle physics? As they say, they can't renormalize the gravitational field. Well, we've developed enough logic to literally say we can change this preposition of the actual logic that the ontology of the subject has developed and say, okay, if we can't renormalize the gravitational field, can we denormalize the gravitational field? Meaning, make it not relevant to fundamental ontology. And again, at the very beginning, we said the presence of these conundrums or contradictions are the evidence that it's wrong, or that the arguments are not developed enough. But so what does denormalize the gravitational field mean? Well, we already have. Gravity is a force. Force is a pressure. We've already proven why you can't deduce past pressure. Again, I'll be able to make a lot more developed physical arguments, but that's true. But again, that's what, right now, any university in the world, that when they say renormalize the gravitational field, they mean, can they take an observation? Can they take their mathematics and look around the room and say, here's where it directly applies to something in the physical world? So that's why we started with this. Again, demonstration on a whiteboard, but literally have 10 objects. And so now we're going to ask the question, can we, or just again, I just wanted to point that out about renormalization. But now let's return back to our 10 ovals. We just have 10 uniform objects. Well, the first thing that I would say is you need a starting point and you need a finishing point. or we have a finite number system working on the function, we have finite alphabets, you don't speak words with 10 million thousand syllables. So now, how about symmetry, right? If I just had 10 uniform objects, how would I group them? The first thing I would do is I would call them an element, and then I would label them, right? But since I need a starting point, and since we're not talking about the universal evolution, right, 0 would be the reference frame. This is trying to connect reference frames to counting, right? I need an initial place. So let's just say I have 2 tree dolls or 2 girl dolls on my windowsill. It doesn't indicate a direction. It's not a unique, right? Physically, chirality and geometry developed the direction, but I would need a reference point to say, where's the start of our counting system, where's the end of our counting system. So for our physical objects, our elements, I would have to label 1, 0. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, that produces the iteration of our base 10 number system right now, right? Add one more element, and you get, you have to write 10. So because of the physical objects being uniform, right, if you get a given temperature, you would need a reference point to start counting, and you need to indicate direction. So let's continue on. So right, you're a little kid, you're reaching around the room, you're trying to feel direction, right? A blind person, how do they feel? Well, or they can't see, so they compensate, they have no visual input. So, but they have to figure out direction, upside down, right? If you go do a flip, you'll start having or a cartwheel out in the sun, you'll have little black spots, your body's used to direction in a way you've never really thought about it. But now that's if I had 10 uniform ovals, that's what I would say and how to label them. And now, all right, we have our base and our range, right? If I look at an object, right, not a uniform object, but I still need a base. The object is the base, and we've said base 3. So let's call our 4th element, or number 3, our 3rd object, sorry. We cross that out because that's the base. Now it's called that's the reference place. And then again, because our geometric arguments, right, 3 and 8 are clearly chiral, or clearly the same object or same symbol. But 3 is our base. For the physical reason, we need an object to interact with light or momentum, and we're going to try to count the set uniquely. So we crossed out 3, and 8 is our limit. So I guess that's the wrong one too. That'll be on 7. But my point is, forget the numbers. If you took from either direction, right now we just talked about direction, if you take the 3rd, start from either side and you put an X to either one, it's going to be on the 3rd object. 6, 7, 8. And what can we say about symmetry? But 3 and 8, again, if you remove them, what do you get? Let's see. Let's do a visual experiment, Brad. 3. 2, 2, all right, we have 2, 4, 2. That doesn't mean anything to me. Groups, but symmetry. If you have a base, objects are our base. Do you count the base, right? Do you count the actual objects? And in the last episode we talked about transitions. So you would have 1 transition, 3 transitions, 1 transition. So I don't know if there was a thing on a windowsill and that happened, that's what I would say. Is the first thing you do is you'd have to, in a local counting system, is label the total elements needed to map the space. There is for sure physical finiteness, certainly to base. There was an initial progression, and I'm very confident there's a finiteness to range. The iteration is what's infinite. And now I do want to respond to one more Lex Friedman had a question at the beginning of his episode, and I'll see if I have anything interesting to say.
Protons and neutrons make up the nucleus of an atom. Strong interaction is responsible for the strong nuclear force that binds them. But strong interaction also holds together the quarks that make up the protons and neutrons. Frank Wilczek, David Gross, and David Pulitzer came up with a theory postulating that when quarks come really close to one another, the attraction abates and they behave like free particles. This is called asymptotic freedom. This happens at very, very high energies, which is also where all the fun is. This is the Lex Friedman Podcast, and here is my conversation.
Asymptotic freedom, independent systems. The thing that pops into my mind when I hear this is how does 3 stabilize? Right, quarks come in 3s because of relative size. What the fuck else did he say? I don't know. Force, strong, weak nuclear, no. How does 3 stabilize at relative size? Right. Describe. How many of you have been through puberty? How many of you have been through the inflation period of the universe? Nobody. So how there's, he said free particles. No, that's logically incorrect. If you have 3 quarks acting as a proton, they are not acting as free particles. They're acting in unity as a single vibration structure, as a single particle. Again, you can't, as is already covered in extreme depth, you can't model force as a particle, period. And then the real structural error is breaking down pressure to force. But asymptotic freedom is a result of independent systems, of the electrons in my foot trying to hit the electrons in the floor, and they're not actually physically touching. That is what asymptotic freedom on a graph, that is what that is doing. But the real question that I got out of there is how did these numbers, elements of a set, particles of a system, constituents of a system, how do they, if you said liberation or free movement, you're talking about an independent system, not dependent on the momentum of another particle in that system. So the language was directly incorrect. But the real question is how does inflation occur, and then how does it stabilize at a bigger size? And how does geometry direct that? How does geometry stabilize that? Right? We're thinking of particles, not sentient beings. So it's got to be a geometric reason, simple iteration, simple geometric reason. But any physical system will grow and stabilize like each and every one of us did. Rapid growth period, and then we stay about the same until we die. That's really all I got out of there, so I'm not going to try to go farther. Thank you for watching From Rhythm to Algorithm, part 47, counting, and keep denormalizing the gravitational field. Thanks for watching. And we can call it the vibrational field, aka temperature. Thanks for watching.